Okay, so let's continue our discussion on the transient analysis of a signal down the transmission line. This is we're still working on the transmission line terminated by resistive load, and for some of the more practical scenarios, and then we discuss the transmission line loaded by reactive component. Okay. Yesterday we talked about if we have a step function. Okay, so step function is we turn the switch on, then we never take off. So once the turn it on, so there's a step, and then the voltage will applied to the transmission line all the time. But we don't have such signals. Okay, you turned on and then never change. And in digital circuit, what most of the time we are encountered is we give a pulse function, right? The pulse function has a certain period and also the pulse width, okay, such as this. Okay, so this is we have this is very ideal rectangular shape pulse function, right? So at the time equal to 0, it turns on, then and then continue for a short period and take and switch off, right? And then maybe after that bit period, and then we turn on again, and then we have turned off. So this become a sequence of binary code, right? For such signals applied to the transmission line, how we deal with this, okay? Then what we can do is we can decompose this into two-step function signal, right? So this pulse function we can consider as a two-step functions and then subtraction, right? So one step function is turned on and keep it on all the time, and another one is we wait for a period of t0, okay, a time t0, then turned on. But however, we turned on a reverse voltage, okay, it's a negative value of v0, right, and then leave it on all the time. Then you can imagine if 1 plus 2 equal to 0, right? Okay, equal to 0, right? So that suggests us we do two analysis using Bond's diagram technique. Okay, one is we analyze this step function, and later on we analyze this step function. Then we superpose the two responses, the output. Okay, according to the linear the linear superposition principle, it should work. You see, because this is the linear circuit. Now let's take a look at an example. So we assume this duration of the pulse is 1 microsecond, okay? And then the time travel from here to here also takes 1 microsecond. So we call this t, right? And let's assume the transmission line with characteristic impedance is 60 ohm. Then we expect we have a reflection coefficient on the terminal side because the terminal is 120, right? And we also have a reflection at a source side because it doesn't match to the transmission line, which is 40. Okay, then we can easily find voltage reflection coefficient. okay? Voltage reflection coefficient on this side is minus 1/5, and on this side is 1/3. All right, okay, is 1/3. So we already said we have repeated this concept many times, right? The voltage reflection coefficient is whatever we see, right? And then minus ourselves, which is say what is difference, right? If this is equal, reflection coefficient 0, right? So we must have something to subtract ourselves, to compare to ourselves, right? We use load, what you see, okay, compare to ourselves, and divide the harmony of these two, right? Summation of the two. So we always using this. So ZL is what we have seen, what we can see, right? Because we always stay in the transmission line. We look towards this side and we look towards this side. We can see two different voltage reflection coefficient. Okay, they play the different role depend on which boundary the wave hit on, right? Okay, now let's study. Let's find a voltage. Let's find the total voltage at the source side. Okay, at the source. How I can reflect the source? Because z equal to 0 is where the source is, right? Where and we don't need to repeat this example because this case we already analyzed before, right? Okay, and we have step function, and when we look at z equal to 0, right? Except at the beginning, how we got 60 volts is because at the beginning we have the circuit is 40. Then what immediate resistance we say is 60, right? Then we have a voltage divider, right? This is V0. So this is initial voltage, right? This is initial voltage. So that is all right. So that is okay. Sorry. Right. Okay. What about voltage is? Okay. Voltage is 100 volts. Okay. We have this equal to 100 volt. Okay. So we have initial voltage at the beginning. We don't experience any reflection yet, right? So we add this at the beginning. So from this point to 2t, right? The wave hit on the terminal and come back. Okay, before that, before two microseconds, we keep 60 volts, right? And then after 6, we have to, I said, let me magnify this. We have to add these two together, okay? We have to add these two together. Then original one, add this 3, we get 76, okay? Then from 2 to 4, we add another voltage and so on, right? So that is this, right? So we can move on. Then we know what is a voltage by okay, then we know the voltage by the first step function. This is what, okay, by first step function input. And then we have another don't forget we have another step function we need to subtract, or we need to add the negative step function starting from 1 microsecond. Okay, start from 1 microsecond. For this case, okay, this is time marker. This is time marker for 1. Okay, 1 microsecond. So that means the same system start perform, okay, by shift the whole diagram on left-hand side. Okay, whole column shift by 1 microsecond downward. So that how we obtain the second one. Okay, second diagram. Okay, second column of diagram. And this case, because the voltage no longer is 100 volt, but become minus 100 volt, minus 100 volt, also by the voltage divider. And instead of the 60 volt, we have a minus 60 volt. Okay, then, and we have add minus sign on every of the signals, either forward or backward, right? And then we use the same bounce diagram method. So we add all this together. Okay, we can show VO2. Okay, the first one is VO1 and the second one is VO2. So the total voltage at Z equal to 0 is VO1 plus VO2. Okay, so that means how to add them together is I plot VO1. Okay, then I plot VO2. Right, because VO2 we use negative voltage, that equivalently we subtract a positive value, right? So right now we just add, okay? We add them, right? So if it between 0 to 1, 60, this is 60, and then this is 0, okay? So we have 60, right? And in this part, 60 minus 60, okay, so that means 0, right? Okay, and for this part, okay, right, this didn't line up well. Okay, let's suppose is this. Okay, so this is a 76, the minus 60, so we have 60. So this is how we add together. Okay, sorry. This should be here, okay, and then move on, right? So this is a 76, and this is a minus 60. This is a okay. This is how we obtain the overall response, okay, by launching a pulse function. Okay, this is how we deal with pulse function. Now, so this is a one step forward on top of a simple step function for resistive load. Okay, so it's one of the practical scenarios. Let's look at another practical scenario. Okay, another practical scenario is if this transmission line is not uniform. Okay, we have one section, we have characteristic impedance is Z01, and with wave speed is Vp1. And we have another part, and divided by, this is the dividing line, okay? The second half is different value, all right? This looks like the scenario when the plane wave hit on a dielectric interface other half of dielectric with different permittivity and permeability, right? And then we know how to deal with that in plane wave. But now we have the same thing, right? But the difference is the media change to a transmission line, and characterized not by permeability, but characterized by the intrinsic wave impedance, characteristic impedance, and wave velocity. So these two, we said, if this is for plane wave, this for transmission line. Okay, plane wave we have mu, we have epsilon, we have mu, right? And we have eta. Okay, for transmission line, what do we have? We have inductance per unit length. We have a capacitance per unit length. We have inductance per unit length. We have characteristic impedance. Okay, so this eta equal to mu divided by epsilon, and then the characteristic impedance equal to R over C, right? And then also we have phase velocity. Here we also have a phase velocity, okay? And this phase velocity in plane wave is this, right? And then in transmission line, the phase velocity is, okay, so you see this is all the behavior is the same, right? Then we are going to discuss next week how the transmission line used for communications. And then in communications, we use a frequency domain model or phase concept. We don't use, we don't analyze the transient behavior. And that is, we have a more comparison, okay, between plane wave and the transmission line. Now, in this case, we can expect when we have a wave hit on the wave, the hit on the boundary, I put the arrow here, hit on the boundary, then we expect have reflections, okay? We have reflections. We already mentioned many times, the voltage and the current are waves, a wave in nature, right? Because they are satisfies the wave equation, right? So they are wave in nature. So therefore, the total voltage is incident wave plus reflected wave, right? Okay, this is the total voltage. Okay, total voltage. And some energy reflect, and then some energy transmitted. Okay, so this part of voltage we call V plus plus. Okay, V plus plus. So that means move forward, keep going. If this transmission line is infinitely long, you don't expect anything bounce back, right? Okay. Until, right, if you hit on a wall, right? So in this case, we can find what is a voltage reflection coefficient, and without, you see, another derivation, right? We can use the concept we learned in plane wave is what I say, the reflection coefficient. Okay, what we can expect is what impedance you see minus impedance of yourself. Okay, then you add the impedance you see, right? So this is the voltage reflection coefficient when you stand in the long line, and okay, when you look at here, right? But if you look at here and then looking into the interface, then the voltage reflection coefficient will be different, right? So if I call this is backward, this is a forward, okay? This is forward. Then this is a impedance for transmission line 1 is what you see, right? Okay, then you add them, right? So this you can say is a minus forward. Okay, so reflection coefficient depend on where you view it. Okay. Okay, where you view it. Okay, what direction you view it. Then without further ado, so I don't derive this. Okay, we can find reflection coefficient when you stand in transmission line 1. Okay, and similarly, this transmission coefficient related to reflection coefficient is a 1 plus reflection coefficient. Okay, we already have this conclusion before, right? And for the current reflection coefficient, this is voltage equal to minus current, okay, minus current. So we don't repeat this anymore. So now let's look at another interesting, okay, more complex scenarios. Yes, first, let's look at the impulse response. Okay, impulse response, and both in time domain and in frequency response. What is impulse? Impulse is if I have a time axis. Okay, if I have a time axis, right, then at any t0, if I launch a delta function, if I say if this value equal to 1, this is called unit impulse function. Okay, this is the unit impulse function. So I guess you have learned this in what signal and systems, right? So anybody give me a response? Have you learned this? Delta function, impulse function. Okay, good. Thank you. Yes. So now let's consider impulse function when t0 equal to 0. Okay, t0 equal to 0. Okay, when t0 equal to 0, I launch a unit impulse voltage source. Okay, voltage source, which is this. Okay, voltage source. The transmission line we have. The first section, let's assume the first line 1, 50 ohm match to the source. So that means if I look at the reflection coefficient, okay, looking toward the source, that equal to 0. Okay, we all talk about the voltage. Okay, then how about the other end? So the line 3 is also 50 ohm, and I put a matched load. So is this terminal reflection coefficient equal to 0? All right, so the reason is I try to keep it simple. Okay, I keep it simple, and then we can look at the essence of multiple reflection between interface. Okay, between interface. Okay, good, thank you. Right, but the line 2, line 2 with different characteristic impedance, and also the velocity is different. So that means, okay, we can say the time from this point to this point that takes 2 microseconds. Okay, and from here to here also 2 microseconds. So every section takes 2 microseconds. So this is our problem. Let's try to find, okay, the voltage. Okay, try to find the voltage at the source. Okay. No, sorry. Try to find output voltage. So the voltage we collect here. Okay. This is the voltage. Let's move this. We try to find. Okay. The computer is slow. Okay. Let's find the voltage across terminal. Okay. And let's find not only the time domain voltage, but also frequency domain response. Now, let's start. The voltage first, when the impulse starts, the source can say 50 ohm and 50 ohm. So that means we have half of the voltage applied to the transmission line. So that means the initial, this equal to 1/2 of the delta function. Okay, 1/2 of delta function. So that is we have 1/2. Then once this impulse hit on the first interface, we have transmit the voltage reflection coefficient of 1/3. So therefore, the transmission coefficient is 1 plus reflection coefficient, right? So it's 4/3. Okay, it's 4/3, right? So 4/3 times 1/2, we have this. Okay, right? So let's just trace the waves. Let's just trace the wave. Okay, so this is already after 2 microseconds. We hit on the boundary, right? And after another 2 microseconds, we hit on the second interface. We also know the second interface is minus 1/3. So therefore, the transmission coefficient is 2/3. Okay, so we multiply 2/3 by 2/3. Okay, this is this. Okay, so this equal to 2/3 multiplied by the transmission coefficient. This equal to 2/3 times 2/3 times 4/9. Okay, this is how we obtain this, right? So this is that means it here is already 4/9, right? So this signal keep moving another 2 microseconds, reach to the load. Okay, has no reflection because it is matched. So this is the signal we reached. First signal we reached is this. Okay, this how long it takes? This is 2, another 2, another 2, right? So total we have a 6 microsecond. This means microsecond. Okay, it takes 6 microsecond time delay, right? Then we reach the magnitude 4/9. Okay, 4/9. So this is the first. This is the first. First wave arrived. It the terminal. Okay. Now, let's say the first reflection. The first reflection back to the source, because the source is matched, so has no further signal coming back. Okay, so this is advantage of we can keep the problem simple, right? So now reflection 0. Okay, then however, the second interface also has a reflection coefficient 2/3 multiplied by reflection coefficient of 1 is minus 1/3. Okay, so this value is 2/3 multiplied by reflection coefficient. This is equal to 2/3 multiplied by 1 minus 1/3 is okay. We have one reflection coefficient and hit on this wall, and then has a reflection again. Okay, then we have a transmission again, and this reaches to here. How long it takes is 2. Okay, let's see, 2, 4, 6. Okay, plus first another 2, 4, total is 10 microsecond delay. Okay, so that is 10 microsecond delay, right? With this magnitude, okay, and so on. Then you can move on, right? Have another reflection and so on. But maybe at this moment is, if you can get 3 of this, it's already clear. Okay, it's already clear enough. It's clear enough, right? 6, 10, 14. So it's every 4 microsecond, you can expect 1 impulse response. So this distance is 4. This is 4, right? Okay. Now let's add them up. Okay, so sorry, this slide is I added last night, and I just asked the TA to update this. Now, this is the output we have. Okay, we can write it in a geometric sequence summation. Okay, geometric sequence summation, but this is not really, this is not really a geometric sequence. Let's just put there, this is not geometric sequence because we have a time delay. We have time delay, we have a delta function. If we only look at this is a geometric sequence. Okay, but now this is just infinitely long sequence composed by delta function. Okay, composed by delta function. So in this case, if we like to find the frequency domain response, what that means is, okay, I changed my input voltage. I changed my VG, okay, by a single tone harmonic function, single tone, right? This is single tone. You see, the cosine omega t, what that is, this is in phasor. If I write it in phasor, is like this, right? So phasor equal to what? So phasor equal to what? Right? So what is the response? Okay, if I apply this, what is the response? The good thing is because the impulse response, because this is impulse response. This is impulse response. Impulse response is a very, very important response of a system, right? We must learn this in signal and system, right? So how to describe a system is if you can measure or you can calculate impulse response, then that means you can get any response. You can get a response for any input because any input, right? Any input is, this is a frequency domain response, right? Then with your excitation, right? So you do convolution, okay? This is impulse. This is impulse response, okay? What we obtain is a very valuable thing, okay? Don't look down at, oh, it's just idea impulse response, so what? It is very valuable. This X is arbitrary input, arbitrary impulsing. Okay, now we have this. We assume this is become cosine omega t. So what is the matter is doing the convolution. Okay, I don't repeat how to do the convolution. The lucky thing is this is a delta function. Okay, delta function. So the convolution is delta function has a very important feature, right? So if you have integration, if you have delta function multiplied by any function, okay, so this equal to, we call a sampling principle, right? So the delta function has a property for the sampling, okay, for the sampling. So if you change the t by tau, right, change t0 by t, so we can simply obtain the response is we replace delta, simply replace delta by cosine omega, okay, because we use sampling principle, right? And with this is not convenient to calculate. Okay, this is not convenient to calculate because trigonometry function. And this is now is the time we can take advantage is the phasor. We learned phasor, right? The phasor form of this, okay, we can write in exponential function, which we already used, right? We write in the exponential function, then we know if I take a real part of it at exactly equal to my original instantaneous response, okay? So this function is easy to add because this is exponential function, and I also have n and n in exponential term. So this tends to be geometric sequence, okay? And the infinite terms, and we know this is 1 minus q, right? And then with magnitude, okay? With the magnitude, so this is a q, okay? This is q. Then we can obtain this in phasor term. This is a phasor. Then you can say the phasor is a very important tool, right? The phasor term. And I just don't have time, so. Okay, anyway. So if you look at this phasor term, you can have a certain phase when this equal to 1, you get, you see, because this magnitude equal to 1, right? So we don't need to worry. This magnitude equal to 1. So when this equal to 1, you reach to the largest value, okay? Then we have maximum equal to equal to 1. It's a magnitude equal to 4/9 divided by 1. Okay, so this is a 4/9, but okay, so we have a maximum value. We have a maximum value, the magnitude. Okay, so the one this when this equal to -1, okay, so we have the minimum value of the magnitude, okay. Okay, so that equal to this. So what we expect is this signal, we have a ripple. We have a maximum value is 0.5. The minimum value is 0.4, okay, in frequency domain. So because once this change, that means the frequency change, okay, the frequency change. So once the T0, right, so the T0 is the, okay, we call this, you call T0, right? This we call, this 3, T1, T2, T3 add together, so we call T1. Oh, sorry, I didn't copy this part, T1, T2. Okay, I will find out what is the definition for this T1. So that means what we expect in frequency domain, if we measure at the load, because of the multiple reflection, okay, multiple reflection, we expect to receive a signal in a ripple, okay, with a ripple, and we can easily find what is value, okay. Okay, now let's take a break. So then we continue to find more applications of the transient analysis. Okay. So let's resume at 10:30. Okay, so I just went too quick, and there are very small things I should mention. Okay, let's see this 4 times 10 minus 6. Basically, what that means is if we assume the time in this section is t1, this section is t2, this section is t3. Okay, so this 4 basically is 2 times t2, right? Okay, because this is 2 microsecond, right? Then this is a term. This is a term when n equal to 0. This is the initial time, right? So the initial time for the signal travel t1, t2, t3, right? So this basically is t1 plus t2 plus t3. Then this is this term. Okay, this is this term. So this is this term, right? Then you can see when we write in a summation, I call this t0. So the n only dependent on how many multiple reflection in t2, right? So this is why we have t2 here, right? Why we have t2. So this axis is a frequency. That means, okay, that depends on my input signal frequency, omega, right? So once this forgiving system, right? Even though your frequency change, but the wave velocity that inside the substrate, that is determined by the media itself, by L and C, right? So the Vp is 1 over L and C, which is independent to the frequency. Okay, so the velocity of wave travel down the transmission line is not dependent on the frequency. Okay, so once the frequency of the input signal change, you can see the ripple. This is why in microwave circuit measurement, okay, if you didn't do a matching very well, you expect your response, say for example, that filter response that's supposed to look like this, okay? But if your matching at the 2N doesn't do a very good job, okay? So you expect to have measurement result when this say this is the transmission coefficient, okay? When this is say 30 dB low, when the signal is very low, very weak, you can see the ripple because reflection is a very small amount, but however, at the superpose on your signal, then you see the ripple. So in future, when you do the measurement and then in frequency, okay, then you see the ripple and very likely you'll have a multiple reflection happen inside, okay, happen inside. So that's why you see I propose this slide. I think it's worthwhile to discuss in our class, at least let our student have some flavor. Okay, what is a system function impulse response, right? And then what is a frequency domain response compared to time domain response? Okay. Now let's talk about another application, okay, of of impulse response or pulse response. Okay, we call time domain reflectometry. Okay. Okay, so the reflectometry, we use reflectometry to diagnose this. What happened? What problem? Okay, for example, we have a very long cable, and then somehow some place is broken. Okay, but we don't know where it happened. Okay, so I need to detect what is wrong with this. Okay, then I send the signal. Okay, so then after a certain time, I reflect a signal. From this reflection, I try to identify what is the problem. Okay, sure, you see, oh, this case is very real happened, right? This transmission line, and then we have something wrong. You see, for supplying the raw oil, okay, from for example, from Russian to somewhere in China, or from Russian to Europe, okay, that is 100 of kilometers, or even 1,000 kilometers, okay. Those pipes, it may have leakage, right? You may have something wrong, you never know, right? But how to detect it, okay? People also use weight, to detect abnormality, okay, what happened, okay. Similar principle of reflectometry, okay, reflectometry. So let's see what is a basic system diagram for such time domain reflectometry. Okay, we have a pulse generator. So we generate a pulse. The pulse is relatively narrow. Okay, relatively narrow. So the pulse is very narrow, and then after a long time, and then send again, and send again. Okay, the reason we have a long period is I need to make sure the reflection happened before the second pulse launched. Okay, so that's why we can easily identify the problem. I don't like to say all the reflection put together, so very difficult to identify. So I have a pulse generator. Okay, then this pulse generator launched, okay, to the system on the test. Okay, but however, what does this mean? Okay, matched attenuator. This function is pretty much similar to this. Okay, I have a transmission line with matched internal resistance. Okay, so that means once the wave hit on coming back, it never can reflect back again, right? So there's many ways we can realize this. Okay, many ways we can realize it. We call matched attenuator. Okay, so that means internal source always matched to the system. Okay, then we have another part of the signal goes this way. Okay, this basically is an oscilloscope. Okay, or you can call display. You can call is a monitor. Okay, the monitor, we have a probe. We have a probe with high impedance. Why we need to have a high impedance? Why we need to have a high impedance? Because if you have very high impedance, but on this side you must have impedance. Okay, as long as you have a current, you must have impedance, right? So this become a current divider, right? So if you have high impedance. So that means their original current goes through this probe. This is a detector, okay, but have no actual signal go into the display. So that means the display here is invisible. Is invisible by the system and also by the pulse generator, okay? But only visible to you. You can see, you can detect the voltage. You can detect voltage, but without perturbate the original current. So that is what the system is. Okay, now let's see how it works. Let's assume, okay, we have a transmission line. We have a transmission line with this section 4 meters long, okay, and the other section 6 meters long, and then connect with short circuit, okay, and somehow, okay, the whole transmission line with impedance is 60 ohms. Even though I didn't mark what is the internal one, but because we have absorber match circuit, so this must equal to 60. Okay, so that means the reflection coefficient equal to 0. Okay, but however, you see, if we have in the middle, we have a connection of 120 ohm, okay, which is this is abnormality, okay, which is what we don't want to say, okay, what we don't want to say. But however, you can imagine if we have a pulse hit on this before reach to the end and coming back, I couldn't say it, right? So this is equivalently to, we have a equivalent to this system. I have this transmission line, this 120 ohms in shunt with 60 ohm. Okay, what's that equal to? Okay, so that is 60 times 120, 60 plus 120. Okay, right? Oh, sorry. So this is 180 and 60 times 120, right? And what's that? Okay, so that equal to 40, right? Okay, that equal to 40. So this whole thing is replaced by this, okay? Replaced by this. Now let's look at this system. This is a simplified system. Then this system, the reflection coefficient, okay, equal to minus 0.2. Okay, I don't give details. 0.2. Now let's how we propel our pulse. Okay, our pulse has a duration 10 nanosecond. You know, one nanosecond equal to second. Okay, second. If it repeat frequency is very low compared to this, right? Compared to this. So that means this pulse I propelled is like this. So I really don't need to worry about this. So this tells you this is far away. This is far away. Okay. As long as I can find, okay, the time return, okay, how long it takes, right? For 4 meters go and coming back with, okay, with 1 second is, let's see, with this speed, then we can measure how long it takes is 4 meters divided by this velocity is 2 times 8, right? So what's that equal to? If this is 0.2, this become 9, right? So that means or nanosecond. This is t, right? This is t. So what that is? This is equals to 20 nanosecond, right? Equal 20 nanosecond. So now let's take a look. Let's take a look at this. What we do the first, the signal, because no reflection at the beginning. So the total signal is applied. We have 1 volt, okay? We have 1 volt. So after 20, this is a 20. Okay, after 1 t, right? So this is like a 20. Why is this in microsecond? This is. Sorry, I think this is wrong. This should be nanosecond. Okay, this should be nanosecond, not. Okay, yes, this is right. Okay, this is right. This is nanosecond, so this is not a microsecond, right? So after first 20 nanosecond, it reached to our load. Okay, reached to our load. Then we have a reflection coefficient of minus 0.02. We have that much energy reflected. Okay, then and lost that much duration. Okay, lost that much duration. Okay, then that takes. There are some waves. Transmit. Okay, there are some waves transmit. This transmission coefficient multiplied by 1. Okay, reach to another reflection coefficient, which is this reflection coefficient equal to -1 because of short circuit. Okay, so we have a reflection coefficient and a certain energy transmitted, and then with negative value of this. Okay, and also not reflection coefficient. So we have multiple reflection in this region, but however, we really don't not interested in this. Okay, we're not interested in this part because we have initial pulse, we have a first reflection, which is only occurred by this. Okay, and this reflection, even though we have infinite number of reflections, right? Okay, but from this reflection, reflection is already determined by the reflection coefficient. Okay, reflection coefficient. This is already enough for us to detect. Okay, to detect what is this value and how long of this distance is. Do you agree? How long this distance is? So therefore, you see, if we know the signal we launch is 1 and we receive signal is 0.2, right? It's 0.2. So we know the reflection coefficient must calculate in this way. Okay, we can determine what R is. Okay, what resistance R is, right? What resistance R is. This resistance R is this. This is R, is 120, okay? This is 120. And also from this duration, this is our t, right? And then we know the speed. We know the speed. We can identify the location, which is 4 meters, So even though we did this analysis, the pulse response, but however, we can only need to make good use of the first response. This part, okay? This part, that is the most useful part. Okay. All right, so this is a very brief introduction about reflectometry. Right? I don't know. The time to me is very precious, so I don't know how much we can finish. That is. Okay, now let's come to this session. Is if we connect the end of the transmission line not by a resistor, by a reactive component. Reactive component means the element is either capacitor or inductor, or the combination of capacitor and inductor, or combination either in series or in shunt, right? In this case, what happened? Okay, in this case, what happened? Let's do quickly. Okay, we have 25 minutes or 30 minutes. Okay, now let's say a time instant. Let's consider a simple case is a step function. Okay, because step function is the simplest case. Step function, we turn it on. Okay, turn it on. That means time, the voltage turned on with V0. Okay. Then I simplify the problem is I assume the characteristic impedance equal to the source impedance. Okay, that means not reflection. Okay, then how much voltage applied? Half, right? Because voltage divider half. Okay, in this case. Then the voltage turned on, so this step basically is a move on. Okay, with time goes, move on. Then because this is before reaching to the end, this is still traveling wave, right? Because not reflection. So for traveling wave, current is just divided by characteristic impedance. So this is easy to know. Okay, now after the t time, okay, after t time, the wave, this is t equal to t. Okay, so the wave reached to the end, we have a total voltage. Total voltage is this, right? We have incident wave, which is V0 divided by 2. And then we know we have a reflection voltage, but so far I don't know what is this, but it must exist, okay? Then not only voltage, but also current, okay? The incident current is voltage divided by characteristic impedance. And also we know we have reflective voltage. If I only look at the reflective voltage, it is traveling wave. So I can divide characteristic impedance to obtain current, right? So this is no question about it, because individually they are traveling wave, okay, individually. So we have a total current, we have a total voltage, okay, total current, total voltage across inductor, okay. We have inductor, okay, have a current, have voltage. Okay, this is inductance. Okay, we know the relation. We know the relation of current and the voltage across inductance is, okay, this is the definition. Okay, this is definition. Okay, no question about it. This is definition. Okay. Then we have this definition also give us another important information. Okay, another very important information. What information is this? If you look at this, I guess 90% of us will say, oh, very clear definition, right? This define relation between current and voltage, right? There is another information. It's very useful to us. Is because we use the derivativity of current with time. What kind of function that you can take derivativity? Ask yourself, what kind of function you can take derivativity? The derivativity, if this function is a differentiable function, this function must be continuous function. Do you agree? Okay, must be continuous. That means the current, okay, at the t minus equal to a current at t plus. Okay, so that means at the, if this is time axis, if this is t, then the current, okay, at t minus, and this point, the t plus, they must be continuous. If not continuous, you cannot use this. You cannot differentiate, right? But we need to use this property. We need to use this property, okay? Now, let's say the at time t, at z equal to L, okay? We have voltage, we know, okay? We have a voltage, but we also have a current, okay? We also have a current. This current, we know this current equal to this, okay? So equal to this. Before we do the analysis, we have to consider this is an initial condition problem. Okay, we assume the current goes through the inductance at t minus equal to 0. No current going through this. Okay, no current going through this. Okay, then okay, no current going through this. Okay, this is our initial condition we must have. Okay, this is, we assume the initial current going through inductance is 0. Okay, this is our initial condition. Okay, now at t, that means this is, I should say, is t plus. Okay, this is t plus. We have this current value. Okay, symbolically. Okay, now let's see, what is this? This is a definition, right? This is definition. I didn't do anything. I just use first. This is a first principle. I keep saying use first principle to solve problem. Okay, if you don't know how to use first principle to solve problem in this subject, then you don't know how to use it for other subject, and then you will be difficult. Okay, if ask you to solve some problem people never solve, right? Okay, now we apply first principle. Okay, then this is never wrong. Okay, never wrong. Then this equation simply is this equation. This equation gives us a very simple way, very simple description about reflected voltage. About reflected voltage, this is the first order. Differential equation. Okay, first order differential equation, right? First order differential equation, but if you look at first order differential equation, we have equal something which is not equal to constant. That means this is inhomogeneous differential equation. We know inhomogeneous differential equation solution is composed by two terms. One is homogeneous equation, one is steady state solution, right? Okay, so that means, okay, let's talk about this later on. We need to solve this equation, okay? To solve this equation, we need to know initial condition, the initial condition. We make use of initial condition on current. Now it's time you ask yourself, why we choose current to apply initial condition? Why we not choose voltage? This answer the question is because we use this relation associated to the current derivativity. And because current, if you can take a derivativity, that means current must be continuous. Okay, all this are first principle. Okay, I rather like to spend more time to teach our students to use first principle rather than tell you, you use this, you use that. You don't have a gun to hunt rabbit. Okay, now we know why we chose current. Okay, why we chose current to apply initial condition. Initial condition, this is for T minus, this is for T plus. Okay, for T plus, these two current must be equal. Okay, we apply this condition. Okay, we apply this condition, we can find, okay, we convert the current initial condition to voltage initial condition. Okay, we start, okay, you see this is a current, this is a voltage. Okay, this is voltage, right? But we obtain the voltage from the current. Okay, from the current. Why we use current? Because the current must be differentiable, and differentiable means continuous. Okay, so all this is logically makes sense, right? Then we use this as initial condition. That means to solve these differential equations, we know because first order differential equation, we must have a term. This term is a steady state. So that means with the time goes to infinity, you have to have this solution. In this case, at infinity, the derivativity equal to 0. Okay, so we know that what that is. So for the first order differential equation, we know the solution form must be exponential function. Okay, so I don't discuss this. This suppose you should know it very well in engineering mathematics. Okay, our task is to determine the coefficient. Determine the coefficient A using initial condition. So how to use this? We substitute time t by capital T. Okay, we substitute this into this and using the initial condition. Okay, we can determine A is this. We substitute A, we obtain this. Okay, we obtain this. Then we obtain the reflected wave voltage. We can also know reflect the current because it's just divided by characteristic impedance. We said reflection wave and the incident wave, both of them are traveling wave. Okay, so we can obtain current by divide voltage by characteristic impedance. Now we know the reflection. Okay, now we know the total voltage at the load. We cannot simply apply so-called reflection coefficient. We have no reflection coefficient applied to reactive component because we don't know how to derive it. Okay, reflective voltage not proportional to the input voltage by reflection coefficient is no longer valid. Okay, for reactive component, we have to solve differential equation and apply appropriate initial condition. We find the solution for both voltage and the current. Okay, so that is curve. Okay, it is very clear because we launch a step function, right? After a long time, step function become DC. To DC for inductance is just short circuit. So the voltage across inductor short circuit approach to zero. And then for the current at the load, you see, because short circuit, eventually that equal to the voltage divided by the source impedance. Okay, the source impedance. Okay, so that is a one type of reactive circuit example. Okay, the second example I go through quickly. that looks very different. Okay, the reactive component not applied to the terminal, applied to the middle. Okay, the middle of the transmission line. Okay, this middle we assume that equal length. Okay, on the two sections. Okay, so then we assume 150, so that means is the end is a match, and the source is matched to the first section. So that means the reflection coefficient equal to 0, reflection coefficient equal to 0. Okay, to solve this problem, again, because we only deal with one reactive component, so this problem still first order. First order differential equation. Okay, first order differential equation problem. And also for first order differential equation problem, we know the first problem we need to calculate, we call a time constant, right? For this case, the time constant tau, okay? The time constant tau equal to this is for typical problem, the current for such a typical problem, we have time constant, right? Time, okay, time constant. Now we are dealing with the problem is a capacitance now this is 50 ohm, this is 150 ohm. Okay, this is C. So we have a time constant is C times 50 plus 150. Okay, so that is a time constant for this circuit. So this is also we know. Okay, this is also we know. Now we like to find the voltage across a capacitor. Okay. Now we like to use the initial condition. We use what initial condition? We use the initial condition of voltage across capacitance. The reason is for capacitance, the current and the voltage is related to. The voltage must continuous. Physically, the voltage across capacitor must continuous. Okay, but in our problem, our initial condition we assume the capacitance we assume the capacitor is initially uncharged. Uncharged means if you don't have a charge, say if I have a capacitor, if have no charge, so that means no field. Okay, because the field exists if you have a charge, right? If you have no charge, no field, that means the Vc equal to 0. This is our initial condition. Okay, Vc equal to 0, that means this is a short circuit. This is a short circuit at beginning, right? So this is our initial condition we are going to use. Okay, now let's do one thing at a time. If we look at this section, okay. Okay, the first when we have a step voltage, what we can say, what this voltage can say is 50-50. So we have only half of the voltage applied to this transmission line. So we have at the beginning we have 10 volt. Okay, if for 10 volt and the total resistance is 50 ohm plus 50 ohm is 100 ohm, and then and divide this 20 volts. So we have 0.2 amps current go into this, and the voltage applied is 10 volt. Okay, so this is our initial voltage we applied all the way to this. Okay, so the voltage go and come back. One way is 1 nanosecond, so two ways 2 nanoseconds. Before the 2 nanoseconds, this is the voltage what we see. Okay, and then the voltage, we said voltage across capacitance is continuous, but doesn't mean the voltage here at the source at Z equals 0 is continuous. Okay, this is not necessarily true. So we have discontinuity, we have a step jump. Okay, so from this period. From this period, we have something we must describe using differential equation. Okay. Now let's find out what value is this. What value is this? Okay. So sorry, we don't have time. So I need to have another 30 minutes or so to explain this problem. I guess we don't have time to finish that, but you know, it's this. My teaching philosophy is I really don't care about how many examples. Okay, what example we how many examples we discussed, and then how tricky the example is. I like to say how we use the first principle to solve problem. Okay, and then also you can independently to solve any problem to using the first principle we have used. Okay, but right now you see, look at the problem we are solving, right? Many of the first principle not necessarily learned in our class. Okay, in our class. You see, for example, you see that what function can take directivity. Okay, derivative is the function that allow you to take derivativity must satisfy the condition of continuity of the function. Okay, derivable function, the basic property that we should learn in mathematics. Okay, and also the definition for capacitor and inductance also we should learn in the basic circuit theory, right? In the basic circuit theory. Okay, anyway, let's stop here today, and we will give some problems assignment that relate to what we have discussed. Okay, but I keep emphasizing we should do assignment by ourselves and try to use the first principle to solve a problem. Okay, if the total time is not long enough, okay, write email to me. Okay, we can, or to Tan Xiao, we can arrange more tutorial time, or if you have a group of students, we can arrange a time that is common to us. Then we can have a free discussion, okay, or not only teach by TA, and then we hope we can learn each other, and then you can also have some voice, okay, to see how you understand the questions. Okay, let's stop here today, and I will be here for next while. And if you like to discuss with me face to face, or you see over internet, okay.